And any of you that are familiar with shape memory alloys or Nitinol know the more you know about it, the more there is to learn. There's lots to learn here. First year that I understand there is an SMA track, and there are lots of great talks, and there are more this morning in the rest of the conference. So I want to thank the organizers for inviting me and giving me the opportunity to be with you here today. My talk is going to be different, probably, than some of the others, because you may note that I am from a faraway place, California, but industry as well. And in industry, we have to make compromises, and we have to make assumptions, and we have to do some things that may be distasteful to many in the room. What I'm here to do is to try to bridge some of the gaps. Right, there are a lot of things that we struggle with in industry, and that we do not have right, and that we would like to do better. And I think a lot of the work folks in this room can help us lead the way. So, just briefly, what is Nitinol? Nitinol is a nickel-titanium intermetallic compound. We often say that it's an alloy because that's a convenient word, but strictly speaking, it is an intermetallic compound, which means that the nickel and titanium atoms, of which there are roughly half and half, need to be in very specific places in a lattice or a matrix for the sort of magic of this material to work. It was discovered at the Naval Ordnance Laboratory in the 60s. When the Navy was looking at different ways to build stronger bombs, basically they were combining titanium with lots of other things to see what works best. Interestingly enough, the place where the material was discovered is now the home of the Food and Drug Administration, the FDA, which studies so many of the medical devices that are made from this material. There are those that believe that it actually came to us from UFOs in the 40s. I'll leave that literature to you to study at your leisure and make your own judgments. The material does have a phase change that it goes through, and there are two primary protagonists here, and there are some others that I'll gloss over. But we deal with austenite, which is the high temperature phase of the material. It feels like titanium. It's kind of stiff and strong. We'll call that the parent phase. And then martensite, which we'll call the daughter phase, is a lower temperature phase. Feels like lead or tin. It's a soft material. And the phase transformation basically cycles between these two crystal structures. So we talk about thermal shape memory and superelasticity. These are both basically, from a thermodynamics point of view, the same thing. In the case of shape memory, we are transforming phases by a temperature change. So if you take austenite and you cool it, you get what we refer to as twin martensite. So those little those atoms kind of twist and fold into this kind of accordion shape without changing the shape, the bulk shape of the structure. And then once that transition has been made, the structure can be deformed very easily with very little stress. Superelasticity is the same thing, but the driving force is the temperature, it is stress. So we can take an austenitic structure, bend it or stretch it or put it under stress, and basically move right to that deformed martensite structure, kind of skipping over the twin phase. So just some terminology. All of this stuff, I have a lot more material here that I'm going to probably be able to present today, but it will be in the PDF that I uploaded this morning, so you should be able to find it. Some terms that are confusing because they aren't super standardized, and when we say things, we often kind of confuse each other. So we try to use these terms, but just to walk you through the basics. The main thing is as we load the material, we're on this upper, what we call the upper plateau here, in terms of stress-strain relationship, and we can endure something like 6 to 8% strain while we're transforming. Once the transformation is fully exhausted, we get into a martensitic phase, and eventually, if we kept going, this would fail like any other material. But if we keep within 6 to 8, maybe a little bit more percent, we can come back and fully recover, and we come back on this unloading plateau. So material has what we call a bias stiffness. This stiffness depends on the direction of loading or unloading, which is a lot more like biological material actually than many conventional engineering materials. So there are some very interesting properties and unique properties of the material, and it's been used for lots of interesting stuff over the years. So since the mid-90s, this is just kind of a number of things that have been published. If you just search Nitinol on PubMed, you can see that interest has been in an upward direction since the mid-90s, not slowing down. What do we do with this stuff? We do a lot of cardiovascular devices. So if you kind of dive into the PubMed data and you look at what's out there, lots of cardiovascular devices, surgical devices. It's really the popularity of this material is driven by the drive toward minimally invasive surgery. So when we need to do big things inside the body through small holes, this material really helps that to happen. So peripheral vascular stents, many of you are familiar with these. This slide I put together 10 years ago. There's lots more of these nowadays. Endovascular aneurysm repair. This is like building a ship in a bottle, a surgical graft that gets basically built inside a diseased aorta. These things are supported by, in many cases, nitinol wire or stent structures that prop them open. One of the newer applications that's got a lot of interest is heart valves, aortic valves, mitral valves, structural heart repair devices, many of which use this material as well to support the valve structure. Common theme here: these are all high performance devices, where in often cases it's your health is at stake. In many cases, life is at stake, and fatigue is a critical design limiting factor for these devices. Another popular area recently is stroke treatment. So devices to either prevent stroke or to retrieve clots from the brain to basically cure ischemic strokes. So in this case, again, the challenge here, these devices are super small. So the size of these features are really tiny. And unfortunately, for all of the cases that I showed you and others, these things break. They still break, right? We're here to talk about fractures, and fractures still happen. We've been working with this material, advancing the state-of-the-art, designing for many years, and we still see fractures. In peripheral vascular stents, we've seen them for many years, and depending on who you talk to, 20 to 30% of cases actually have fractured stents. Endovascular aneurysm repair, again, there have been reports of fractured stents leading to degraded performance of these devices. Heart valves, also a lot of anxiety about the potential for fracture in heart valves, and some reports of actual incidences. And normally we talk about high cycle fatigue with these devices because they're in the body for years, 10 years or more. But low cycle fatigue is also an issue, and this was just in the news about a month ago. And this is an electrophysiology instrument. It's not an implant. So in this case, these devices are failing within tens or hundreds of cycles as this device is trying to map a beating heart. So all of these things, the devices are used in ways that are very challenging. You can imagine this giant spherical thing gets packed down into that very tiny catheter, right? So you can imagine where that little red circle there, which is where the fractures are occurring, the strains are extraordinarily high. All right, so what can we learn about why this happens or how we can do better? And we're going to look at a few frontiers, okay? And we'll see how many we get through. But the first one we're going to talk about is boundary conditions. Okay? I'm going to start with a kind of a silly example, so forgive me, but for this audience especially, what's better for fatigue, a steel band or a rubber band, right? This is kind of a silly question, but it kind of motivates. This is an example that I use with folks that are not fracture experts, but it kind of motivates the issue here, which is that it depends on the loading conditions, right? So for a load-controlled environment, you want a steel band, obviously, because the rubber band is going to snap. In a displacement-controlled or strain-controlled scenario, you want a rubber band because because the steel is going to deform. And Nitinol fits somewhere in between these two paradigms. It kind of has features of both. It has both kind of aspects to it. So are Nitinol medical devices stress control or strain control? Well, it depends, right? So in the heart, you've got a beating heart here. If you're in a coronary artery or an aorta or something, you're pretty much, you're mostly in a pressure-controlled environment, though you have displacement limits that needs to happen within. If you're a stent that's in the leg, behind the knee, you're really dominated by displacement control, right? Because there's no way to avoid the fact that when you bend your knee, that stent is going to have to bend along with it. So you're really dominated by displacement control, but you have stress to worry about as well. So really, we have both of these things happening. But the challenge is we have this plateau where we kind of go through a wide range of strains with really very little change in stress. So in industry, kind of years ago, we decided that we were going to just sort of ignore stress. And that's a little bit of a strong term. We don't completely ignore it, but in most of the characterization that we do and that we use, we kind of don't think about stress, and that leads to some problems. There's other things that we don't think about too. This takes us to another frontier, which is the application-specific nature of this material. So again, it's inconvenient, an inconvenient truth of sorts, but this material has an application or kind of history dependence to it, right? Where all of the things that are listed here, I won't read them all, they all matter. So the history of the material, the history of the process, how we process the material, how the material got to be in the first place, from ingot to tube to wire or whatever. All of those things affect the mechanical properties and ultimately the fatigue properties of the material. And we can't, it's very difficult to capture all of these in our models. So we try, and we'll look at what the typical workflow that we'll use to help our customers kind of work through this stuff in industry. And basically what we try to say is, look, you're going to make a device, that's what you care about, but in order for us to predict the lifetime of this device, we need tensile properties, so we need tensile specimens, and we need fatigue properties, so we need fatigue specimens. And then of course you need a finished device because that's what's going to matter to the patient. We need to make sure that all of these things use, to the extent possible, the same material, the same process, the same surface treatments, and have the same strain history. And you can do that for tensile specimens. It's not that hard. I want to point out something here that's going to be important later. When we do tensile specimens, dog bone specimens, or whatever, we really try to make sure that we understand what's the strain that the actual device is going to see when we use it. So it's a stent that's going to be crimped into a delivery system and then deployed. It's going to get to some pre-strain out here before it cycles. So we're going to put our tensile specimen through that same kind of training before we do our tests, and the same thing for fatigue specimens. So tensile specimens, we get some data that looks like that, very nice. We get some numbers, we plug them into our FEA code, and we can do an analysis. Now we need to make some fatigue specimens, and we have some choices, right? We can do rotary bend fatigue testing, we can do tensile testing, or we can make a surrogate specimen. They all have their pros and cons. Rotary bend fatigue testing is convenient, it's easy to do, a good way to collect a bunch of data and to compare materials, but it's not representative of many of the devices that we actually use. It's representative of, let's say, an orthodontic file, but it's not representative of a stent. So unfortunately, we can't really use that. I'm going to skip tensile. And really what we'd like to do is we'd like to use little pieces of our devices themselves, right? But they're complicated and messy. They have small feature sizes. We can't really grip them very easily or conveniently. But they have this kind of complicated stress state that's some combination of bending and other things. So what we'll do is make these surrogate samples that try to mimic what the actual device looks like in terms of its dimensions and loading characteristics. And then we'll test those, and then we'll create an SN plot. And in our case, the S stands for strain. We'll look more at this a little bit later. And because of all these other mean strain effects and other things, we try to represent the results in something that looks like this. We call it a strain limit diagram, or constant life diagram, where we take the result of each of those fatigue specimens, and we decide, is it a fail or is it a pass? And we color our symbols, open or closed, and we plot mean strain versus strain amplitude, and then we try to draw some kind of a line through there and set a criteria. There are problems here. There are a lot of problems. Among them are these different symbols represent different types of samples. Some of them are tension samples, some are diamonds. You don't know what the history is of these. So it's hard to take this data and extend it and understand how it applies to your particular device. Okay. So, brief aside, we talk about how we make the sausage. I'm going to quickly go through how we do a lifetime analysis so you can see how ugly it is. We're going to make the sausage. So we're going to use a simple example of a basic generic stent, which looks like this. You can download it if you like. There's a link there. And we need to decide what type of boundary conditions. This is really the hardest part. This is a whole hour talk unto itself. But for now, let's just say we're going to do something behind the knee, so below the SFA artery, kind of SFA popliteal condition. And we're going to assume some loading condition. What we're going to focus on here is a bending condition. So we're going to make a stent. We're going to expand the stent. And we're going to make sure it looks like the thing that we actually manufactured, which it does. And then we have an expanded state. We're going to crimp it down. We're going to deploy it into the vessel. And then we're going to put it into a bend. And then we're going to relax it. So the fatigue case that we're studying is basically this right here, which I'm animating with the slides. And we're going to now look at a mean strain plot and a strain amplitude plot. And we're very kind of crude simplifications here. We're looking at the principal strain scalar of these, basically, between those two frames. And if you zoom in, you see that strain amplitude is very localized. There's these little hot spots. All right, so what we're going to do is take the results of this, look at the mean strain and strain amplitude at every one of these points, and we're going to go back to our friend the strain limit diagram here, and we're going to plot the value of the mean strain and strain amplitude at every one of those points on a plot that looks like this. And then we're going to say something. It's either good or bad. It's going to fail or it's not. And we'd like to try to calculate some kind of a safety factor, but you really can't. There's no way to do that. Okay, we struggle, and our customers struggle, and the FDA struggles with this. Don't have a good answer. So I'd like to talk about some ways that we can maybe improve and do a better job of saying something meaningful about those results and predicting risk. And this story is going to look at the material itself, and it is going to then try to compare what we see in the material with what we see in the design. Okay, because the intuition here is that in the material we have some distribution of inclusions, little specks of impurities that exist in some spatial distribution in the material. And in the design, we have these hot spots, these little red spots, that we see in our FDA, and they exist with some volumetric distribution within the design. And what we kind of feel intuitively is that it's the intersection of these things, which is where we see fractures, right? It kind of makes sense. So part one is the material impurities themselves. It's been observed by most people in this field that when these parts fracture, when components or test specimens fracture, I say almost always, but it may in fact even be always, they originate at these surface inclusions or voids. We just see it all the time. It's all what happens. So what does ASTM or standards have to say about these inclusions? Well, they're specs, right? They talk about a mass percentage basically that's allowable, and some area fractions in milled product and bars of this stuff. But the specs, as they currently stand, don't have anything to say about the size or shape or distribution of these impurities in finished material that we use to actually make devices. So we're left without guidance there. the industry's done a lot of work to improve the purity of materials because we believe that that's going to do that's going to make for better devices. So, there's a picture here. There's basically all the folks that are making material have versions of pictures that look something like this. And we find, in fact, that higher purity material improves fatigue performance. Not surprising. And in fact, as was presented earlier this week, a smaller inclusion size improves fatigue performance. So all these things intuitively make good sense. So the hypothesis here that I'm trying to get at is that we have this variation in materials and methods, in the ways that we make material, and the way that the impurities get into the material. We have variations in the impurities themselves and how they're distributed, and that's a big part of what explains the scatter that we see in fatigue results, and why we still can't, or why we still fail to predict, right? Why we still have these clinical problems, and we have not kind of solved this thing. So it would be nice if we had a way to have a three-dimensional volumetric characterization of the impurities that we see in different types of materials. And we can kind of approximate that from some of the data that's available from 2D metallurgical cross-sections. But you have to make some guesses about how to transition from the second dimension to the third. So it would be nice if we had a better way. And how could you do that? You could take a whole lot of slices, which would be quite time-consuming. Or, as we heard, I think in the first plenary lecture of the conference, you can use X-ray technologies. And I think it's pretty clear, and there's been some unpublished work that shows that you can use a beam line and very high-powered X-ray to see inclusions inside of nitinol material. But what we're looking at is it possible to actually use some of the latest commercial tools, and the results are are promising. So this was a demonstration that we did recently on a little piece of a nitinol component that's a test sample that's roughly the size, has feature sizes of stents and things like that. And you can actually see voids and inclusions quite nicely, and you can actually take slices in any arbitrary plane that you like, and you can map the entire volume of these things and characterize the volume of those things. And we're working on that, work in progress, but we think that we can get something like a fingerprint out of this, so to speak, and some fundamental characteristics that describe the distribution of particles in the materials that we use. And then if we have that distribution of particles from the material, now we need to think about the design and the load case for the particular design. And in fact, there are some others that have presented at this conference in previous years that are on the same track. So there's a group, I think in the Roe Institute, that did this work in Sweden, and they're looking at a more simple case of a test specimen, and they're looking at quantifying the stressed volume and then comparing that with the particle distribution that they're seeing from X-ray, and then drawing some conclusions about fatigue lifetime by comparing those two populations. So that's exciting, and we're trying to find ways to apply this in our domain of nitinol medical implants. So one of the things that we need, we have these complex structures, right? So this is just a simple example. It happens to be one of those little diamond samples where we are looking at the strain amplitude distribution. And what we've done is written a little code that can go in there and measure those volumes, measure the volumes of material that exceed some critical threshold. And the code for that is there, so you can find it, and if it's useful, I'd be delighted to hear from you. But you can use that and now get to some kind of volumetric probability plot for your design, which I'm showing here. And it, of course, depends on where you set your threshold, which is another question, which we can get into, but you set your threshold somewhere, and you get some volumetric probability for your design and loading condition. And this is in the same terms as the volumetric probability that we saw for the material that we calculated earlier. And now we can put those two things together and do some math, right? And actually get to something like a percentage or ppm risk of these two things overlapping with each other. And this is a model that it's still in development, we're still working here, but that can hopefully get us to something that can help us to predict fatigue lifetime as a function of material purity and the distribution of critical stresses within our design. We got 2 minutes? Yeah. Okay, so let's go to here, and let's look at pre-strain. This is some work that we are doing back in California, and we are beginning to understand that pre-strain is something that has a big influence on fatigue performance of these materials. And it's been studied and published, but the gist of it is the more strain you put in to your device, it causes your plateau. It changes your plateaus. So the higher you go up on this curve, when you come back down, your curves are dropping. So your plateaus are dropping. The material is changing as a function of its strain history. So we've done a bunch of testing on tensile samples. The characteristics are here, where we vary pre-strain, mean strain, and strain amplitude. And what we see is that we can see this influence. So right here, we're looking at the low pre-strain group, and I've taken the basic SN diagram and binned it out here by different levels of mean strain. But you can see, it's working, here we go. You can see basically where we're at there. And then if I go to the higher pre-strain levels, you can see that as we increase the pre-strain, my threshold is increasing. So we're actually getting a benefit in the material by increasing this amount of tensile pre-strain, which is kind of confusing, but it's very clear that it's actually happening. So we've tried to do some statistics and take a look at this, and we see these trends. Certainly, we have increasing fracture probability with strain amplitude, but we also see the trend with pre-strain. The statistics aren't super compelling. We've got more work to do, but there's definitely a signal there. So what is the implication of this if we bring it back to our simulation and point clouds and such? So if we take a point cloud, normally we don't think about pre-strains when we look at our point clouds, right? So we might see something that looks like this for some example case. But if we take our point cloud and divide it up amongst different levels of pre-strain, we might see that those little points in the cloud look something like that. Okay? And if now our threshold is changing as a function of the pre-strain level, it may predict, in fact, what my prediction is about what is the most critical point or what is the most critical condition in this design. So the critical point may shift as a function of this pre-strain, which is a little bit concerning, which means we really need to be worried about it. Okay? So there is this third dimension, if you will, in addition to mean strain and strain amplitude, that we need to think about, and that I encourage researchers in the field to worry about as well. I'm going to skip this, and finally, go to the final frontier. Okay, I cannot talk here without mentioning constitutive models. I can barely begin to understand what is going on with constitutive models, I promise you. I have great admiration for those of you that work in this area, but what I want to impress upon you is that we are still living in 1997. Okay, Princess died, just died in a crash, and we are stuck in 1997. So thank you, Arusha Taylor. And there's been a lot of great work that has happened since then. We've got to get beyond it. We've got to look at critical strain methods, and Smith, Watson, Topper. There's some talks here talking about some of these things, and there's some great work that is being done in Germany and elsewhere. So just a couple of the papers there to stimulate that. We are very eager in industry to have better constitutive models that are more accurate. Finally, I want to thank you and invite you all to California next year, SMST, for those of you interested in this field. The call for papers is now open, so I hope to see some of you in San Diego this year. Thank you. Thank you very much.